All right, continuing on. In this lecture video, we're going to look at examples of applying the estimation procedures that we looked at in the previous lecture. In particular, we'll look at estimation of the individual treatment means. We'll then look at estimation of differences between pairs of treatment means. We then generalize that to looking at estimation of a general contrast of two or more treatment means. We then generalize it further to look at estimation of a non-contrast linear combination of one or more treatment means. And then we'll consider estimation of the treatment effects from the effects model, and I'm going to ask you to do that as an exercise. So let's first look at estimation of the individual treatment means. Now, before any type of treatment comparisons can be made, we have to be able to estimate the individual treatment means. So we're going to use the techniques covered in the section on estimation to compute point estimates as well as confidence interval estimates of the individual treatment means. So using the formulas for the variance of the point estimators of the individual treatment means, we see that the estimated variance of each of the estimated treatment means is going to be equal to 1.40764. The square root of that gives the estimated standard deviation associated with the point estimate for the individual treatment means, and that is equal to 1.186440053. Now, if we were going to display these, we could round those, but in doing the computations, I'm going to use the full precision so that we get the most accurate result possible for the confidence intervals. Now, in order to construct the confidence intervals, we need an interval coefficient. And because this is not a contrast, the interval coefficients have to be approximated. The number of degrees of freedom associated with the interval coefficient is unknown, and so it has to be estimated. And so remember that there are two approximation methods that we are using to obtain approximations to the interval coefficient. This is the first method, method 1, or approximation 1. And we saw the formulas in the section on estimation. I'll refer you back to that note. And so to calculate the approximation, we have these values that are called Q, Q1, Q2, and Q3. And in this particular situation, for estimating the individual treatment means, Q1 is equal to 0.04, Q2 is the same, and then Q3 is equal to 0.12. Now, using these values along with the mean squares from the ANOVA table and the indicated t-values in the formula for the approximated interval coefficient, and you can see the locations of those t-values down here, it turns out that when we plug these values in, that the approximate interval coefficient for an approximate 95% confidence interval estimate of the individual treatment means, that approximate interval coefficient is given here, 2.619929397. And again, in doing the calculations to get the margin of error, and then using that margin of error to get the lower and upper endpoints for the intervals, I'm going to use the full precision of these values. So once we have the approximate interval coefficient, we then would multiply it against the estimated standard deviation of the point estimates of the individual treatment means to get the approximate 95% margin of error associated with each of the mu hat sub k's. And that approximate 95% margin of error turns out to be 3.108389173. And so then we can use that along with the point estimators of the individual treatment means to get the lower and upper endpoints for an approximate 95% confidence interval for each of the individual treatment means. Now, using Satterthwaite's approximation method 2, what we do is we approximate the degrees of freedom, and then once we have that, we look up a t-value corresponding to those degrees of freedom. And so here is the formula for the approximate number of degrees of freedom. Turns out to be 9.475085696. And so the approximate interval coefficient, the upper 2.5 percentage point for this distribution with this many degrees of freedom, is 2.244984524. And so then we take that approximate interval coefficient, multiply it against the estimated standard deviation of the mu hat sub k's, and we get the approximate 95% margin of error associated with the mu hat sub k's, equal to 2.6635395558. And so we have these two approximation methods that we're using for demonstration purposes. In practice, you would pick one or the other. And you would probably pick one that is available in the software that you would be using. Satterthwaite's approximation would typically be the choice if you had to choose between these two. And so when we utilize those two approximations to get the interval coefficients and the corresponding margins of error, we are able to calculate these approximate 95% confidence intervals. And so in this column here, the second column under point estimate, I've got the actual point estimates for the 5 treatment means. And remember that they're labeled here, and in the indexing we're using 1, 2, 3, 4, 5, but that corresponds to A, B, C, D, and E as was originally used in the description of the experiment. So mu hat sub 1 is 35.76. That's the estimated treatment mean under treatment 1 or treatment A. And then for treatment B, we have the estimated treatment mean of 35.04. 35.68 for the estimate of the treatment mean 3 or treatment mean C. For treatment mean 4, equivalently treatment mean D, we have a point estimate of 34.9. And then for the, remember this is the control, treatment 5 or treatment E, the treatment mean for that treatment is 29.16. And you can see that's quite a bit different than the others. The other 4 treatments are active treatments. All right, remember this is strengths of insulators, tensile strengths of insulators made from 4 different compositions, clay compositions. And treatment 5 or treatment E was the control. And so the question is, are there any differences between the active treatments? It certainly looks like there may be differences between the active treatments and the control, although to make a formal decision we have to test that or construct confidence intervals. But numerically, these seem to be fairly similar and somewhat different than the control. Now, notice that for both of these approximation methods, I've listed here the approximate 95% margin of error associated with these point estimates. And so using approximation 1, where we approximate the t-value directly, rounded to 4 decimal places, the approximate 95% margin of error associated with these point estimates is 3.1084 for each of those 5 point estimates. For approximation method 2, which is Satterthwaite's approximation, rounded to 4 decimal places, we see that the approximate 95% margin of error associated with each of these point estimates is 2.6635. So it's somewhat smaller than the margin of error obtained using approximation 1, and so these intervals are going to be a bit more precise. All right, so from that standpoint, these would be better intervals. All right, and then using the point estimate and each of these approximate margins of error, we come up with a set of confidence intervals, one using approximation method 1, and then one using approximation method 2. All right, and so for demonstration purposes, again, I'm including both of these. In practice, you would typically just use one. Now, notice that there is a great deal of overlap between all of the first 4 intervals, and even the 5th interval overlaps with, it looks like at least 2, so 2 of these. It overlaps with this one, and it overlaps with that one right there. However, trying to determine whether corresponding treatment means are different by looking at individual confidence intervals is not the most powerful way to do it. But we can look at that and just get an idea of where there's overlap. And we have the same kind of result here, although because these intervals are a little bit more precise, they're a little bit narrower, we can see here that the interval for the control which ranges from 26.4965 up to 31.8235. That does not overlap with any of the confidence intervals for the 4 active treatment means. Okay, now I wanted to show you here how I came up with the interval coefficient for approximation method 2, Satterthwaite's approximation. All right, we first approximated the number of degrees of freedom, and if I go back here to method 2, approximation method 2, we see that this was the approximated number of degrees of freedom, 9.475, 085696. And so that's what I have entered into this wizard on the TI-84 calculator. So what I'm using is the inverse T functionality. And so you would go to the distribution menu. You get that by pressing the second key and then the vars key, and that brings up the distribution menu. And then you would scroll down to option number 4 for the inverse T, and that brings up the wizard. And the area here, this is a left tail area. So if we want a right tail area 0.025, we would subtract that from 1, all right, to put in the area field. And we could either just do it mentally and enter 0.975 here, but I've explicitly shown taking the difference 1 minus 0.025 just to show you that you can do that as well. And then we enter in the approximate degrees of freedom, which was 9.475, 085696. Press the enter key, and that pastes that function into the calculator display. And then press the enter key again, and that returns the t value, the interval coefficient for that particular number of degrees of freedom and the left tail area here. So 2.244984524. And again, that's what we got right here. All right, now another way to obtain the interval coefficient is to use SAS. And so here what I'm doing is I'm going to use the T inverse function. All right, so it's the same kind of function, although the name is just a little bit different than it was in the calculator. All right, and the arguments to this would be the left tail area, again, and then the number of degrees of freedom. And so you do this in the context of a data step, and then once you have that, then you can use proc print to print out the contents of that data set, which contains the one observation, and the variable for that observation is the interval coefficient, the t value. Now by default, they are rounding this to 5 decimal places, but in the internal memory, it is represented using double precision, so it's a very, very precise number that they're using. So if you used it in subsequent calculation, it would be using the full precision of the value that's being retained in memory. All right, now let's look at estimation of differences between pairs of treatment means. So in order to come up with point estimates for the differences between treatment means, we would need the point estimates of the individual treatment means, and that's why we looked at that first. Okay, now we'll look at estimating differences between pairs of treatment means. And so the first thing we'll do here, before we calculate the estimates, let's calculate the variability associated with those estimated differences. And because we have equal replication, the variance of the differences between pairs of means will be the same for all pairs of means. And using the formulas given in the section on estimation, we see that the estimated variance for an estimated difference of treatment means is 1.22664. The square root of that gives us the estimated standard deviation of the estimated difference between pairs of treatment means, and that turns out to be 1.10753781. All right, now in this situation, because this is a contrast, the interval coefficient is known. It comes from the t-distribution, and the degrees of freedom are known. They are equal to 12, all right, which is p minus 1 times p minus 2. And again, we want the upper 2.5 percentage point from that distribution. And so using the t-table that we have, that would turn out to be 2.179. So I'm using the t-table whenever I can, and if I'm not able to, if I have to look up a value for a number of degrees of freedom that are not in the table, that's when I'm going to the calculator or to the software. So once we have the interval coefficient, we can obtain the 95% margin of error associated with the estimated difference between treatment means by multiplying the interval coefficient and the estimated standard deviation. And so that turns out to be 2.413324888. So that's the margin of error for the confidence intervals that we'll be constructing. And so then in this table, what I've got are the 10 pairwise differences. There are 5 treatment means, and so there are 10 pairwise differences. And I've used the point estimates that we looked at in the previous subsection to come up with these estimated differences. All right, and so you can see those values here. And then as we calculated on the previous slide, all right, we see that the 95% margin of error associated with each of these point estimates is 2.4133, rounded to 4 decimal places. Now, in this particular table, this is the same for the previous table that we looked at, where we had the margins of error and the confidence limits. I've actually entered this full precision value, all right? And then I've just indicated in this table to round those values for display purposes only to 4 decimal places. So, and then what I've done is these are actually calculated cells, just like a spreadsheet. And so to get this value, what this cell is doing is it's taking this estimated difference and it's subtracting this margin of error. So it's doing the calculation using full precision and then rounding the display value to 4 decimal places, but internally it's retaining the full precision of each of these quantities. All right, and so you can see here that we asked the question previously, which of these treatment means are different from each other? All right, when we looked at this, when we did the first example 4.1, where we did the analysis of variance, we concluded that the null hypothesis for that ANOVA was not true. We rejected that null hypothesis. There was strong evidence of differences between means, differences between treatment means, and the natural follow-up question would be, where are the differences? Now, because we have some structure here to the treatments, in that the first 4 treatments are active treatments, and the 5th treatment is the control, perhaps the primary interest would be checking to see are there differences between any of the active treatments and the control. But it may also be of interest to determine are there differences between any of the active treatments. And so looking at, let's answer that first question first. Are there any differences between any of the active treatments and the control? And so that's going to be a comparison with treatment means 1 through 4 with treatment 5. And so if we look at this comparison here, mu1 minus mu5, we see that the estimated difference is 6.6. The 95% confidence interval for the difference ranges from 4.1867 up to 9.0133. Notice that 0 is not in this interval, and so that we would conclude then that treatment mean 1 is different than treatment mean 5 at the 0.05 level of significance. Comparing treatment 2 to treatment 5, we see a similar result in that the 95% confidence interval does not contain 0. And so that tells us then, because of this equivalence between two-sided confidence intervals and two-sided hypothesis tests, we know that we would reject the null hypothesis that treatment means 2 and 5 are equal, all right, and conclude that they're different. Looking down at a comparison of treatment mean 3 to treatment mean 5, that estimated difference ranges from 4.1 up to 8.9 approximately. That interval does not contain 0. And so again, treatment mean 3, we can conclude is different than treatment mean 5. And then finally, the comparison between treatment mean 4 and treatment mean 5, that interval does not contain 0 either. And so we would conclude that treatment means 4 and 5 are different as well. So we can see here that each of the active treatments is different than the control, and in particular, each of the active treatment means is greater than the mean of the control. Now let's look at the second question. Are there any differences between any of the active treatments? And so let's first look at comparing treatment mean 1 and treatment mean 2. That interval contains 0, and so we would not be able to reject the null hypothesis that the two treatment means are equal at the 0.05 level of significance. Comparing treatment means 1 and 3, again, that confidence interval does contain 0, and so we are not able to conclude that a difference exists between treatment means 1 and 3. Comparing treatment means 1 and 4, again, the confidence interval contains 0, and so we would not be able to conclude that a difference exists between treatment means 1 and 4. Next, comparing treatment means 2 and 3, that interval contains 0, and so we could not conclude that differences exist between treatment means 2 and 3. Comparing treatment means 2 and 4, that interval contains 0 as well, and so again, we are not able to conclude that a difference exists between treatments 2 and 4. Now looking at the comparison of treatment means 3 and 4, that interval contains 0 as well. And so we can see that there would be insufficient evidence at the 0.05 level of significance to conclude that treatment means 3 and 4 are different. So what can we conclude based on the initial ANOVA and these pairwise comparisons? Well, we've concluded based on the ANOVA that there are differences among the 5 treatment means, and then based on these pairwise comparisons, what we can conclude is that there is not a significant difference among the active treatment means, but all of the active treatment means are significantly different than the control. And so that's a lot of information that we've been able to glean from the data from this experiment. All right, and so that's very helpful to think about. All right, now that leads us into the next type of comparison that we might want to make based on those results, estimation of a general contrast of 2 or more treatment means. And so the researcher is interested in estimating the difference between the arithmetic mean of the active treatment means and the control mean. And this type of comparison could very well have been specified before the experiment was run, which would be the ideal situation, so that we're not doing comparisons that are suggested to us by the results, which inflates the overall type 1 error rate. All right, so what we're talking about, but what we see here that it does make sense because we're not able to conclude that differences exist among the 4 active treatment means. So that suggests that perhaps there is no difference and that therefore there is a common value for the 4 active treatment means. But regardless, even if they are a little bit different, it makes sense here to compare the arithmetic average of the 4 active treatment means to the control mean. And so this is the way that we would do it. mu1 plus mu2 plus mu3 plus mu4 over 4. This is the arithmetic mean of the 4 active treatment means. And then we're going to compare that to the control mean, and we do that comparison through the difference. All right. So we can see here that the coefficients for this comparison, this linear combination, are 1/4, 1/4, 1/4, 1/4, and -1. And when you add those up, you get 0. So this is indeed a contrast. Note also that we'll need the sum of the squared coefficient values. And so when we do that calculation, we get 5/4. Okay, so the point estimate for this linear combination, and again, it's a contrast, is 6.185. So that's the difference between the arithmetic average of the active treatment means, their estimates, and the estimate of the control mean. So this is the estimated value of the difference between the arithmetic average of the 4 active treatment means and the control mean. Next, we want to be able to construct a confidence interval for that comparison, for that difference, for that contrast. But we need to first calculate the estimated variance and standard deviation for the point estimator. And using the formula given in the notes, All right, we see that the estimated variance for that linear combination, that contrast, is 0.76665. The square root of that gives us the estimated standard deviation for the estimate of the contrast. That estimated standard deviation being 0.8755855,184. All right, the t-value, the interval coefficient for this confidence interval, it's going to be a 95% confidence interval. That interval coefficient comes from the t-distribution with 12 degrees of freedom, and in particular, it's the upper 2.5 percentage point of that distribution. And so using that along with the estimated standard deviation of the contrast, we come up with the estimated margin of error associated with the contrast. And that is, let me say that again, the estimated margin of error of the estimate of that contrast. That's the product of the interval coefficient and the estimated standard deviation. And so we get 1.907900845. Okay, so once we have the point estimate and the estimated margin of error, we can come up with the 95% confidence interval estimate for that contrast. I have approximate here. I should not have that. In fact, let me go ahead and take that out. Okay, so I'm not going to call it an approximate confidence interval because, and again, let me go back here, because we know the true value of the interval coefficient. All right, so I'm reserving the word approximate when I talk about the confidence interval to those situations where we have to approximate the interval coefficient. All right, so anyway, doing this calculation, the estimated difference between the arithmetic average of the 4 active treatment means and the control mean is somewhere between 4.277 approximately up to 8.093. So I've got the full expressions here for display purposes. If we were going to put this in a report or a homework set or an exam, obviously we would round that to a certain number of decimal places, but I just wanted to display the full precision here so that when you do these calculations, you can compare your results to what I'm getting to make sure that you've got no calculation errors. Okay, so that is how we would estimate that particular contrast. Now let's look at estimation of a non-contrast linear combination of one or more treatment means. And so what I want to do is estimate the arithmetic mean of all 5 treatment means. And you'll remember that this quantity, which we're denoting by mu, shows up in the effects representation or the effects form of the statistical model for the Latin square design. Right? So we've been working primarily with the means model representation, but there's also this representation that is actually the representation that's typically used in software like SAS, and that's the effects model representation. All right, so we want to estimate the arithmetic mean of all 5 treatment means. Now, this can be written as a linear, it's a linear combination, and it can be expressed this way, where each of the A's is equal to 1/5. Now, when we add those up, we get 1. Obviously, that's non-zero, and so what that tells us is that this linear combination is not a contrast. And so because it's not a contrast, what we know is that the variance and the standard deviation for the point estimator for mu is going to involve all of the variance components in the model, right? And so it's going to make calculating the estimates of those variance and standard deviation quantities more complicated. Now, the point estimate for mu is just that same linear combination, but of the point estimates of the individual treatment means, and that turns out to be 34.108. All right, now using the formula for the variance of an estimator for a non-contrast linear combination, we get the following formula, all right, with the values plugged in. So the estimated variance of mu hat turns out to be 0.916984. The square root of that gives us the estimated standard deviation of the point estimate of mu, And so the estimated standard deviation of mu hat turns out to be 0.957-592-8183. All right, now the interval coefficient required for constructing a confidence interval estimate of mu is unknown, right, because this is not a contrast. Therefore, in order to construct the confidence interval, the interval coefficient will need to be approximated. A 95% confidence level will be used. Now, in practice, we would just pick one method of approximation, but for demonstration purposes, for teaching purposes, I'm going to use both methods. And I would highly recommend that you do these calculations yourself to get the practice. Once we approximate the interval coefficient using each of those two methods, then we will construct confidence intervals for mu using each of those approximation methods. And so let's look at approximation 1. First, note that we've got the three Q values, Q1, Q2, and Q3. Go back and look in the notes, you'll see the formulas for those. And for this particular linear combination that we're estimating, Q1 is equal to 0.04, Q2 is the same, and then Q3 is negative 0.04. In addition, this approximation method requires us to use three t-values, and so the t-values are 2.776, 2.776, and 2.179. And so plugging those values, along with the required mean squares from the ANOVA table, into the formula for this method, we get an approximate interval coefficient equal to 2.855860072. Now that we have that, we can multiply that against the estimated standard deviation of mu hat to get the approximate 95% margin of error associated with mu hat. And that value is equal to 2.7347511086. Finally, taking the point estimate along with this approximate 95% margin of error, we get the approximate 95% confidence interval estimate of mu, which ranges from about 31.373 up to 36.843. So again, do this calculation on your own to make sure that you can get that. Compare your results to mine and see what you get. Now let's look at approximation 2, which is again called Satterthwaite's approximation. And so with Satterthwaite's approximation, what we're doing is we are approximating the number of degrees of freedom associated with the true interval coefficient. And so the values for Q1, Q2, and Q3 are the same for this approximation method as they were for the approximation method 1. And it turns out that the number of degrees of freedom, the approximate number of degrees of freedom associated with the true interval coefficient, whatever it happens to be, is 4.223490097. And so the approximate interval coefficient is then the upper 2.5 percentage point of the t-distribution with that number of degrees of freedom. And that turns out to be 2.719452277. Now that we have that, we multiply that against the estimated standard deviation of mu hat. That gives us the approximate 95% margin of error associated with mu hat, equal to 2.6041-27962. And then once we have that approximate 95% margin of error, we subtract it from the point estimate mu hat, we add it to the point estimate mu hat to get the lower and upper endpoints for that approximate 95% confidence interval estimate of mu. And that ranges from about 31.504 up to about 36.712. So very, very similar intervals, but the approximation method 2, Satterthwaite's approximation, gives us a little bit narrower interval, right? The margin of error is just a little bit smaller, so the interval is going to be a little bit narrower. It's going to be a little more precise, All right, and that's typically a better thing. All right, now, again, I just wanted to show you how I came up with the interval coefficient using Satterthwaite's approximation. Once we had that degrees of freedom, which was 4.223490097, and so I'm again using the inverse t function on the TI-84. And again, this is the inverse of the CDF, the cumulative distribution function. And so this, even though we want the upper 0.025 percentage point, we have to express this as a left tail area, so that would be 0.975. So before, I had 1 minus 0.025, but I can also just do that calculation in my head and enter that value there. It'll take it either way. And so then we come up with the t value here, 2.719452277, which was what we listed before. So that's one way to get it. The other way to do it is to again use a software package like SAS, for example, and that's a very easy way to get it as well. Perhaps not quite as easy as using the calculator, but it is easy to use. It's not a complicated SAS program at all. And you can see here that rounded to 5 decimal places, we get the same value. All right, now let's talk about, just briefly, about estimation of the treatment effects, the alpha sub k's, k going from 1 to 5, that are part of the effects model, the effects representation of the model. And so again, we've been working primarily with the means model parameterization of the Latin square model, which is given here, okay? And what makes this the means model representation is that I've got the mu sub k here. Okay, that's the population treatment mean for the units receiving treatment k. Now, we also can represent the model, the statistical model for the Latin square design using the effects model parameterization. And what that does is it decomposes the mu sub k into mu plus, in this case, tau sub k. So mu is the overall mean that we actually just estimated in the previous example, or in the previous subsection, and then tau sub k would be the offset from that, right? And that offset is called the effect, the treatment effect. All right, the treatment effect is the difference between mu sub k and mu. All right, so what I want you to do is, as an exercise, estimate the treatment effects, the alpha sub k's, for each k going from 1 to 5, associated with the effects model parameterization. Now, for the purposes of this exercise, I want you to get practice doing this by hand. When I say by hand, what I mean is using non-statistical software means. So obviously use a calculator or use a spreadsheet or something like that. I want you to, the point is I want you to implement these formulas. I want you to go through the process of implementing, thinking about what it is you want to estimate, implementing the estimation formulas for the point estimate, also for the estimated variances and standard deviations, the estimated margins of error, and so forth, and then construct the confidence intervals. So I want you to do all of that by hand, okay? And so get that practice. And so I think that'll be good. Okay, so that wraps up this example. It's a fairly comprehensive example. And again, let me go back to the very first slide that we looked at in this particular section. Okay, so here's that slide. And so what did we look at here? Well, we looked at first how to estimate individual treatment means. We calculated point estimates of those treatment means, but we also calculated confidence interval estimates. We then looked at how to estimate differences between pairs of treatment means, both using point estimates as well as confidence interval estimators. We then generalized that to estimating general contrasts of two or more treatment means. And then we generalized that further to look at estimation of a non-contrast linear combination of one or more treatment means. And using that, you can now go ahead and estimate the treatment effects, the alpha sub k's, for the effects model using the results from the means model. The means model and the effects model are related, all right? And you can estimate those treatment effects based on the results from the means model. Okay, so just looking at this list of types of functions that we've learned to estimate, and we're typically wanting to estimate linear functions of one or more treatment means, you can see that this really exhausts the possibilities, all right? Given any kind of linear combination of treatment means that you may need to be able to estimate and make inferences about, it's going to be contained in one of these situations. So go ahead and do the practice, do all of these calculations, make sure that you can do it on your own, all right? Check your work against mine, but then also do this as an exercise that we haven't done in the notes and just see what you get, estimation of the treatment effects for the effects model.